Hello friends, let's watch this video to understand the type of stresses like tensile stress, compressive stress, bending stress, transverse shear stress and the torsional shear stress. So let's begin with the tensile stress which is denoted by sigma T. Let's do an activity to understand the tensile stress. Take a rope and pull it from its two end with a equal and opposite force, due to which the internal stresses will generate and the rope will get break. Let's go for other example. Take a circular rod and pull its two end so that the applied force are normal to its cross sectional area. This is the applied force which are shown, and these are normal to this cross sectional area we can see in the diagram. And you observe that the internal stresses start generating and it will be produced at the unit cross sectional area. For that, we know that the tensile stress when the body is subjected to equal and opposite axial pull force, the stresses produced is called as a tensile stress. Now the tensile stress is given by the load upon area, where W is the axial tensile force we can see from this diagram, and A is the cross-sectional area of the rod. And we know that as it is a circular rod, right? So that's why the area of that circular rod is given by pi by 4 d square. And d is the diameter of that rod. Even the other formula for a circular rod is A is equal to pi r square. Compressive stress, which is denoted by sigma c. Let's take a rectangular bar and push its two end so that applied force are normal to the cross-sectional area, and we observe that the internal stresses are produced per unit area. So when a body is subjected to equal and opposite axial push, so you can see from this diagram, it is an axial push forces and the stresses produced is called as a compressive stress. So compressive stress is given by load upon area. W is the axial compressive force and A is the cross-section area of this rectangle. And with that, if I show you in this diagram, this is a rectangular piece and area is given by breadth into height. And that's why we can say area in this case is B into H. Now, if you take a circular rod, in that case, it is again the compressive stress is equal to load upon area. But in this case, the area get changed, because if you are taking a circular rod, the area of the circular rod is given by pi by 4 d square, and d is the diameter of the rod. Next is a bending stress, which is denoted by sigma b. Now, let's take a plank or a straight beam which is supported at the end and apply the load at the center. The beam get deflected. Now the upper surface or upper fiber from the neutral axis, this is a neutral axis, or here also at the center there will be a neutral axis, goes under the compression. Means the upper fiber goes under the compression while the lower surface from the neutral axis goes under the tension. Now, in this case, what happened when the bending stress, what we are showing that the stresses we generate will be the tensile or a compressive stress. So we can say that when the beam is subjected to a bending moment, that is a M, then the stress induced is called as a bending stress. Now, in this case, the bending stress is calculated by using the flexural formula. You can see from this diagram, I shown that component and the neutral axis with a yellow color line. So it is given by m by I is equal to sigma b upon y. Now m is nothing but the bending moment. So here we are showing the bending moment, and I, which is shown here, is the moment of inertia of the cross-sectional area. Here the cross-sectional area will be a circular what we are taking, or a rectangular. It depends upon that. And sigma b is nothing but a bending stress. And y, which we observe in this diagram, is the distance of extreme or the outermost fiber from the neutral axis. Next is a transverse shear stress, which is denoted by tau. Let's take a two plate, that is a plate 1 and a plate 2, and connect this both the plates with the help of rivets or a pin. Now load W is applied, or it will act towards the left side, and on the plate 2 load is acting towards the right, due to which it gets slide. Because of that, the rivet gets break at the junction in two parts, right? And the means shearing will takes place here. And this is due to the action of two equal and opposite force which act tangentially. Now, when we are talking in this manner, we know that when a section is subjected to equal and opposite force acting tangentially across the section, is here, it tends to shear off. Here we can see the shearing has been taken place, and the stresses produced is called as a transverse shear stress. Now, if we see here, we are talking about the single transverse shear stress, that is tau is equal to load upon area. So W is the force applied tangentially. A is the cross-sectional area of the rivet, as the rivet is circular. So that's why the area of that will be given by pi by 4 d square, means d is the diameter of the rivet. Now let's take another example. Now in this case, I have taken the three plates, plate 1, plate 2 and plate 3, and all these three plates are connected with the help of a rivet. Now in this case, this is an example of a double transverse shear stress. I'll tell you how it is. Now in this case, when you pull it right in a opposite direction, it means that the two equal opposite force are acting tangentially. In that case, this pin is break into the three parts. Ultimately, means shearing is taken at this region, okay, and this region. And that's why in this case, our formula is that tau is equal to P upon 2 into A. Means why it is 2? Because these rivets are just divided into three parts, okay. Means here at one place there is a shearing, and other place here there is a shearing. Means two shearing will takes place, and that's why it is a 2 there. And here also, as I shown that the P is the force applied tangentially and A is the cross-sectional area. As here also, the rivet is a circular one, and that's why A is the diameter of that rivet, which is given by the formula pi by 4 d square. Next is the torsional shear stress, which is denoted by the tau. Now, to understand the concept of torsion, look at this picture. In order to drain the water from the cloth, hold the cloth on extreme end with your hand and start twisting it in an opposite direction. Then the cloth is said to be in a torsion, or I can say the component is said to be in a torsion. Let's take an other example. Now consider shaft, and this shaft is fixed at one end, and and another end is subjected to the torque. We can see here the torque, which is denoted by T in this case. And as a result, on every cross section of this shaft is subjected to the torsional shear stress. Now, in this case, when a component, means in this case you can see the shaft, when a shaft is under the action of equal and opposite couple, that is a twisting moment, then the component is said to be in a torsion, and stresses set up due to the torsion is called as a torsional shear stress. Now, due to the circular section of shaft, it has been considered that the shear stress at the center axis will be always 0, and it is always maximum. If you see in the diagram, at the outer surface of the shaft will be always a maximum, okay, whether it may be a this surface or this surface. So the stresses in such cases will be always maximum on the outer surfaces. Let's deep with the diameter of the shaft. So torsional shear stress is given by the basic torsional equation, that is tau upon R is equal to T by J, where tau is the torsional shear stress, R is the distance of outermost fiber from this neutral axis, which is equal to the d by 2, as D is the diameter of the shaft. That's why the radius will be always d by 2. T is the twisting moment, or we can say the torsion, and J is the polar moment of inertia of that cross-sectional area. In this case, it is a circular one. That's why it is given by pi by 32 d raised to the power 4. Thank you, friends.